Did you think you were gonna get away with just adding and subtracting 273 this unit? Well, guess again. That's right, we're talking about heat calculations. Hit the theme.
Ain't nothing but a chem thing, baby. Two flipped out teachers going crazy. Lancaster is a district that pays me. Unbreakable, so please don't try to break this. But back to the lecture at hand.
Hello and welcome to another episode of SchuFu Chemin at ya. I'm your host Fu, and with me as always is Shu.
Shu know it.
So in the previous lessons we talked about heat capacity, temperature.
And today we're going to show you how to put them all together. Let's get started. Heat calculations, a lesson from the matter and energy unit. What does the heat change depend on? The amount of heat gained or released in a physical or chemical process can be calculated mathematically. The heat change depends on the substance's mass, specific heat, and the temperature change. Remember that heat is measured in joules, not degrees Celsius or Kelvin, so don't assume that the heat change is the same as the temperature change.
Which formula do I use to calculate the heat change? On table T, there are three math equations under the heat section. Only one of them applies to this unit, and that's Q equals mc delta T. The other two we're going to use in a future unit.
Let's break down Q equals mc delta T. Q is the heat change in joules. M is the mass in grams. Capital C is the specific heat capacity, and its units can be joules per gram times Kelvin or joules per gram times degrees Celsius. Delta T is the temperature change. It may be in Kelvin or degrees Celsius. Now when we calculate the change in temperature, we have to go final temperature minus initial temperature. This means that it can be negative.
What's the deal with C? Most of the time, the substance being heated or cooled is water, so the specific heat capacity of water can be found on table B. If you look here, it's at the bottom of table B. If the substance isn't water, the problem will give you the value for C.
Although the units are given as joules per gram times Kelvin, it may be easier to write them as joules per gram times degrees Celsius, since temperature is usually given in degrees Celsius in the problem. This is allowed because a change in 1 Kelvin equals a change in 1 degree Celsius. If you remember from an earlier video, we used the ladder analogy and we said that if the Celsius and Kelvin scales were two different ladders, the distance between the rungs would be equal, they would just be staggered by 273. So we can really think of 1 Kelvin as being 1 degree Celsius in terms of the change. Now you can leave temperature in degrees Celsius and you never have to convert degrees Celsius to Kelvin. Example 1, let's practice applying this new mathematical formula. You ready, Fu?
I am.
If 5.50 grams of water has its temperature raised by 5.0 degrees Celsius, how much heat is absorbed by the water? Let's use the FSA method. All right, so what's F stand for?
All right, so F stands for formula.
What formula would we use here?
All right, well, we just got done going over Q equals mc delta T, so Q equals mc delta T.
Good, let's write that down.
Q equals mc delta T.
Now it's a good habit to circle the variable that we're solving for. So let's look back at the question. What are we trying to find?
All right, so the question says how much heat is absorbed by the water. So how much heat is what the question's asking for. And I know that heat is represented by Q if we look at our reference table. So I'm solving for Q.
Good. Always circle the variable you're solving for. If you want to change it to X, because that's what we're trying to find, that's okay. But we can also leave it as the original variable Q.
Okay.
All right, so S. What's S?
All right. S stands for substitution.
Good, and we have to remember to substitute with units, right?
Yep.
All right, so Q is what we don't know.
So I'm going to change that to X. Okay, so M stands for mass.
Yep.
And I'm looking back at my problem. I see that mass is 5.50 grams of water, so I'm going to go with that. So 5.50 grams.
All right, now C. What is C?
All right, well, it says on my reference tables that C is specific heat capacity, but I'm not seeing it in the problem.
It's not listed in the problem, but there's another clue. What substance are we actually heating up?
Oh, it's water. And on table B, we have physical constants for water, and that's right, most of the time it's gonna be water. So I'm gonna use the specific heat capacity off of table B. And that value is 4.18 joules per gram degree Celsius.
Right. Remember, we can change it from Kelvin to degrees Celsius just to make it easier, because in the problem we have degrees Celsius.
That's right. It says Kelvin on the reference tables. That's why I said it, but it says Celsius in the problem. So I'm going to leave it as Celsius.
Good. Makes it a lot easier. All right. So what is our change in temperature?
All right. So I don't see an initial and final temperature here, so there's no subtraction, but it says the temperature is raised by 5 degrees. So doesn't that imply that the temperature changed 5 degrees?
Good. Exactly. So we can sub that number in directly.
Okay, so 5.0 degrees Celsius.
All right. Looks like we are ready to solve by multiplying.
Okay, so that's the A part. As an answer, I get x equal to 114.95.
Let's try some unit cancellation here.
All right, so I got grams divided by grams, so that cancels out.
Good.
And I've got degrees Celsius divided by degrees Celsius, that cancels out.
Yep.
I don't have anything that cancels out joules, so that's gotta be my unit. Oh, plus it's energy, right? And energy is in joules.
Exactly.
All right, so my unit is joules.
Now we do have to apply the proper sig figs.
Okay.
So
How do I do that again?
Well, we're multiplying, so we want the least number of sig figs. Let's go back to the original problem.
All right, so the data I have is 5.5 grams, 5.50 grams, and 5.0 degrees Celsius. So this one is 3 sig figs, and this one's 2, actually. So if I'm going with least, I should go with 2.
All right, good. So how are we gonna round that to 2 sig figs?
All right, so the first 2 are the 2 ones there, which means I circle the 4, which doesn't do anything to the 1, so I just drop it, right? So 110 joules?
Looks good.
All right, ladies and gentlemen, we're gonna do another example here. Example number 2. Shu, are you ready?
I'm ready.
Okay. If 55.2 joules of energy are released from 1.23 grams of water at 25 degrees Celsius, what is the final temperature of the water? All right, Shu, we're gonna do this FSA again.
All right.
So what does F stand for?
Formula.
And again, what equation or formula do you think we're using?
Q equals MC delta T.
Perfect. All right, so we need to get in the habit of circling what we're looking for. So what's this question asking for?
We want the final temperature of the water.
Okay, good. So where is that in my formula?
Well, I don't see a specific spot for final temperature. I just see the change in temperature right here.
Okay, so we don't have final temperature, but do we recall what delta T, or how you get it? How do you get delta T?
So it's a change in temperature, so we always go final temperature minus initial temperature.
Good, so we can actually change our equation a little bit here too, right? So what's it gonna look like?
All right, so how about Q equals MC, and then in parentheses, I'll label it TF for final temperature.
Perfect.
Minus TI for initial temperature.
That makes sense. Yeah,
Right.
let's go with that.
So the final temperature is what I'm actually trying to solve for.
Awesome. All right, so I think we got our formula good. Let's do the substitution, or S part of this.
All right, so I'm solving for TF, so I actually should have Q this time, right?
Yep.
All right, so remember Q is energy, and it's in joules. So
Perfect.
55.2 joules.
All right, so I'm seeing one minor thing here, all right? It does say that the energy, those joules, are released.
Released. So released, energy is being given off. It's exothermic. So does that mean the heat is actually negative?
It is. Think about it. If you're releasing something, you're letting it go. So it's a negative to you. If you were absorbing it, it would be a positive to you. So it's released, it's negative.
Okay. It looks like the rest is okay. I've got my mass of water, which is 1.23 grams.
Good.
Specific heat of water, again, it's water in this problem too, so I'm going to use the 4.18 joules over grams times degrees Celsius.
Good.
TF is what I don't know, so I'm going to leave that as TF. And then the initial temperature, because it looks like where I started, the water was at 25.0 degrees Celsius.
All right, good. So it looks like we got some algebra now.
Yeah, algebra. Okay, so I know I want to solve for TF. I don't know if I have to deal with the 1.23 and the 4.18 or get rid of the 25.
All right, so like any good algebraic equation, we have to remember our order of operations, right? Our PEMDAS.
Okay, so I think then I want to multiply first instead of dealing with addition and subtraction?
Correct.
Okay, so 1.23 times 4.18 is 5.1414. And to get rid of that, to kind of try to isolate my variable, I'd want to divide both sides by the product of those two numbers. So I'm going to divide both sides by that number.
And again, that 5.1414, that came from multiplying 1.23 times the 4.18.
Good. All right, so I'm going to divide the negative 55.2 by the 5.1414, and I get negative 10.736. And that's going to equal what's left over, which is the TF minus the 25.0.
Good.
All right, so what do I do next? I want TF by itself.
Yep.
So just like before, when I multiply, the inverse operation was division to get the variables separated. This time I have subtraction, so I want to add to both sides.
That's
right?
correct.
So I'm going to add 25.0 to both sides. I should be able to get my final answer when I add. So TF is 14.2636.
All right. Do you think we can be sure of all those decimal places?
We cannot, so
All
we
right,
got to
so
do sig figs, right?
That's right.
All right, so I'm just going to go back to the original problem. All the numbers actually have 3 sig figs. So
Actually, they do.
I can round this to 14 point, let's see, 6 tells me to round up, so 14.3. I do still need a unit.
Okay, so
Well, I do remember that it was temperature, so
what do we measure temperature?
Temperatures in degrees Celsius.
Perfect. You try. Please do this example problem using the FSA method. Please make sure your final answer has proper units and significant figures. A 22.00 gram sample of iron gains 235 joules of energy to obtain a temperature of 88.9 degrees Celsius. What was the initial temperature of the iron? Now, the specific heat capacity for iron is 0.45 joules per gram Kelvin. Okay, ladies and gentlemen, that's going to do it for today's lesson on heat calculations, and it's going to wrap up this unit.
It's been emotional.
Today's episode is brought to you by
Kanye Fromye from IKEA. This picture frame doesn't require a photo. It comes with Kanye's portrait and autograph on each side.
But we never off, always on till the break of dawn. SCIENCE in the hall.